skip completely. I mean, okay, let's just actually not do that. So fine, field of study that gives computer the ability to learn without being explicitly programmed. Explicit program, you provide it with rules, and you provide it with the question, and then it produces like answer. So your program, right? It takes these guys and then it produces the answers, right? In machine learning, it's like sort of reversed. So you have a model, you give it the question, you give it the answer, and then it produces the rules basically. This was on the first slide of my lectures slides. So anyway, next thing, example, digit recognition. I mean, okay, obviously we know that's the classic example, right? The training data set is given by this. Yeah, we understand all of that. I've been around quite a bit of time now, and I get that whole notation thing. Let's just move on. So just erase everything. Or you know what, like whatever. Next, classification is regression classification stuff. Yeah, whatever. Next thing, metrics for classification. Let's just try to recall everything. That was funny. Anyway, the precision is basically this thing. Y is equal to y hat equal to a upon this. So it's basically the amount of predictions that are correct, and this is for one class obviously. So this is basically like the case for one particular class, but if you have multiple classes, once again you can do this thing, no problem with that. But if you want to find the the precision for the whole thing, for your whole prediction, what you should be doing is that, okay, just you find the precision for each class and then you just take the mean of that. Heck, that was having a name. So yeah, like macroscopic average, right? So that's macroscopic average when you just like find the p for each a, and then you just do like summation of pa upon m, where m is the total number of classes that you have. There's a microscopic thing as well, where you just do this thing. So y equal to y hat equal to a, that cardinality upon, so just like sum this up upon the summation of this y hat equal to a thing. So y hat equal to a can also be written in a different way. So since we're like predicting, we're basically talking about the positives, right? Whenever your a is, basically it's going to be just true positive plus false positive. Remember, positive is for the prediction, and true and false is for the is for the y equal to y hat thing, right? So when you say true positive, you mean that you predicted positive and it was that actually it was positive. So cool, that's there. That's just precision. What about recall? Well, recall for a, that's pretty much the same formula. You just have y equal to y hat equal to a upon y equal to a. For the microscopic case of the recall, once again you just have this thing, summation of, yeah, just this whole thing, y equal to y hat equal to a, and this is basically the true positive, basically true positive for a obviously. So true positive upon the summation of y equal to a, which can be written as true positive plus the false negative, I think, right? Because your ground truth is yes, now your ground truth is a, so a false negative is also corresponding to y equal to a, except that y hat is not y. Amazing. So that's done. Next thing, oh wait, you also have to do the macroscopic. So this is microscopic, this thing is micro, this thing is macro. Precision, right? This is a recall microscopically, and then macroscopically it's a summation of RA upon M, the usual thing. Next thing, so that's the metrics for classification. Oh, I missed a few things. I missed the F1 score. So F1 score is just it's just the harmonic mean of the precision and recall. So basically it's like 2 PA RA upon PA plus RA, whatever, for one class obviously. For multiple classes, it's slightly different. Basically, the macroscopic F1 score is basic, so macroscopic average of F1 score. So that's just it. Cool. You got the F1 score. Now F1 score for this, what is it called? The max, basically like you just take the max for each class, right? Am I missing somewhere? No, okay, so you do take the macroscopic, yes, you take the, wait, am I missing something? Yeah, so you take the macroscopic precision for the whole thing, not for each class, for the whole prediction that you have. You take the macroscopic the whole thing, and then you take the SHM of that. Sorry, the right. So this is just going to be like 2p microscopic micro. I don't know how to denote that. So I'm just going to call it PR upon p plus r. That's the microscopic thing, and then summation of score f1 upon m. That's the macro thing. I don't know how to denote it. I'm just going to call it as f1. Next. F1 score. You have Matthews coefficient. So Matthews coefficient is just given by the, so you have this coefficient matrix, right? This thing is the predicted thing. Oh, actually this should be the actual thing. Whatever, doesn't matter. This is the actual thing. This is the predicted thing. You have 0 1 0 1, and then you have all of this stuff, right? The true positive. Heck, that's wrong. Should be 1 and 0 over here. Sorry, I got used to this digital systems thing, so I'm just like writing 0 1 subconsciously. Anyway, so true positive. This is positive versus false. Yeah, this thing will now be negative negative, obviously. Now this is obviously just true negative. This is false negative. Yes, yes, that is the way it should be. So basically, your Matthews coefficient is given by the determinant of this thing, which is like just Tn times Tp minus Fp times Fn upon the square root of the sum of columns and sum of rows, right, individually. So basically just do Tp plus Fn Tp plus Fp, but we know what that is, right? It is the size of the data set, obviously. Sorry, no, it's not the size of the, it's the number of one prediction, and then there are like number of 0 predictions. And so which is, I'm just going to do this thing, y hat equal to 1, and then you have y hat equal to 0. That's just better to like right. So y hat, so y, not y hat, y equal to 0 and y equal to 1. You do that thing, and that's your Matthews coefficient. Cool. Let's just actually see the thing. Yes, so Tp times Tn minus Fe times Fn upon all of that, obviously. Then you have multi-class metrics, which I already talked about, right? The micro and macro thing. Yes, accuracy is the same in like in any case, right? Accuracy is just the y hat equal to y upon the cardinality of y, right? That's for like one variable output. What about like something more than that? So like if you have multi-class thing, then how do you get the accuracy? Well, you just average the accuracy for each class, basically. Alright, next, metrics for regression. You have the MSE, which is the mean square error. For some reason, people use the loss as just the square error as well. Sometimes I don't like that, but whatever. Decision tree for discrete inputs and outputs. Constructing optimal decision trees and P complete. Very hard, basically. Yeah, that's non-polynomial. Anyway, so constructing optimal decision trees is hard, but you can do that using the ID3 algorithm. That's not considered optimal decision trees. That's just doing a greedy algorithm thing. So that just like gives you one tree, which is okay-ish. Okay. Usually you create an approximation using some greedy algorithm. Find, choose nodes. Right. This is the entropy formula. Yeah. The entropy formula comes from this thing that suppose like, you know what, I'm not gonna explain it. Learn it on your own. So negative log xi is called the self-information. Fine. Thus the entropy is the expected value of the self-information. Makes sense. It's just log of this guy and then p of that, right? Something is very wrong. Negative log of xi is called, no, it should be p, right? It should be p of xi. Yep. Okay, I can't do that apparently. Fine. So negative log p of xi. Oof. So xi is just a class, by the way. Cool. Interesting. See, I just have the probability distribution of xi, in this case in the mass function. Fine. The log of that, negative log of that, sorry. That's a function of xi in the end, right? Doesn't matter how it looks or whatever. So that is the self-information. Cool. The maximum entropy of a 2-class classification has a maximum of 1. And what about n-class classification? When in n-class classification, this is optimized whenever your so you can do this Lagrange multiplier thing, and then you will find this that this is optimized whenever your pxi is 1 by n. So this should just be n times negative n times the sum of well, this is 1 by n, then you just have natural log or log base 2. I don't know, I'm just gonna use natural log because I do that. I just, yeah, anyway. So of pxi, okay, who am I kidding? We're doing a computer science thing, so it should be just log base 2, right, which I'm going to call just log. So log of p, which is basically just 1 by n again. So this just becomes like summation of something's messed up. Yes, this n thing is yeah, that's from the summation. So it's just this, right? So this cancels. You just get like log of n. In case of n classes, you will have log n as the maximum entropy, right? Okay. The reduction in entropy using an attribute v that takes value in a equal to v1 that's given by this thing is called the gain, and it works not just for entropy but for anything, really. Anything that's sort of an intensive property of the data set. Yeah. We recursively add attributes to the branches. This is the ID3 algorithm that we are describing when we say we recursively add attributes to the branches, right? The S varies depending on what branch of the decision tree you are trying to select an attribute for adding another node. If entropy of S equal to 1, we stop adding node to the branch. We could also use another criteria called the Gini index, or we could use the MSE as well, because we have used that in one assignment. In any case, the Gini index is given by 1 minus the summation of pxi squared, basically. So yeah, entropy is given by this weird looking thing, which is just the expected value of self-information, which is just negative log of p of xi. Gini index is given by 1 minus summation of pxi squared. And MAC, you know how to do that. Then you have the ID3 algorithm, which is, okay, I've written down the algorithm basically. Create a root node. So let's just follow along and see how this works. You create a root node. Cool. just move on. So then you have, in fact, so you have the metrics for, that's the IDP algorithm. Cool. Decision tree for discrete input, metrics for regression, multiclass metric, Hatchie coefficient, F1 score, recall, precision. That's something I should put up. So, right. So coefficient matrix is not like a metric directly, but you could get a lot of information from that. So yeah. Okay. Metrics for regression. This decision tree for discrete inputs and outputs. We did this. Why am I opening this? Okay. Bias and variance. We did that. Dummy classifier. Yeah, we know what a dummy classifier is. It is something that gives random outputs, or just gives the mean of the data set or something like that, right? So that's a dummy regression thing. So this would give a mode basically, right? So outputs the mode of the target of the data of the training data set, and this outputs the mean of the target of the training data set. Now you get to like some cool parts. So ensemble learning, or ensemble learning, or however you want to pronounce this thing. So alright, so you saw that a decision tree is prone to overfitting, right? So you cannot increase the complexity a lot, because after a point it just starts to fall, right? The accuracy starts to fall. So how do you make it reach a better accuracy in that case? So the answer is, like, you train multiple decision trees, and then every decision tree will be sort of overfitting to basically data sets which are independent, as in they describe different features. Yeah, that's just the way to call it, of the main data set, right? So maybe you have something like I don't know how do I say this thing. Maybe you are trying to figure out whether or not you are going to pass one particular exam, and the parameters to do that is the number of hours that you spend learning, and I don't know, maybe your IQ. Just some like random example anyway, and let's just say that your IQ is not correlated at all, or something like that. Yeah. So what we'll do is we'll this isn't a good example for this, because ensemble learning doesn't work like that. This is so it's okay. This is would also work with it. So it captures the ratio between predictor, and then the final predictions that you get, you just like take the mode of that. So right now this is 2, so it isn't possible to be taking a mode, but for an odd number it would be, and so that is your actual prediction, right? In case of a regression task, maybe you just have z equal to x plus y, so it captures the relationship between x and z, this captures the relationship between y and z, and then you just take the mean of these guys, so that gives you the thing, right? Yeah, who knows, maybe x and y coming from some sort of a probability distribution, and then things could take a turn for the better. We don't know, but whatever, right? So that's just the way ensemble learning works. You split a data set into multiple, you train these different trees on, or different models on these data sets, and then whenever you want to predict, you just take the average or the mode of the actual like predictions from each tree, basically, right? So first let's go to the cons. So increasing number of trees doesn't always increase the accuracy. So by the way, why is this done? This is done to reduce the variance. Yes, I told you, right, like decision trees overfit very easily, so we want to reduce the variance, and that's why this is done. It's basically like capturing all sorts of different relations, so that if the decision trees do overfit, we'll have some sort of an average like thing, and that will hopefully generalize, right? Okay, so what are the cons? Increasing the number of trees doesn't always increase the accuracy. So 0 times 100 is still 0. So like if all the decision trees work really bad, well, yeah, so in the end it will just work bad, right? Yeah, but the probability of the decision trees working bad is actually very low, in fact. Oh wait, I think that's not the thing. Alright, okay, so there are two things. First is like your decision trees do not work very well, right? And second, so it does not increase, that is it. It's not saying it's going to give you bad accuracy, it's saying that it does not necessarily increase the the, what do we call it, the accuracy, right? And I don't think this example is correct over here. I should not be doing this. Okay, as the trees need to be trained on datasets which are uncorrelated. So this isn't the issue that they're talking about. The issue that they're talking about is that if, so over here you see that the datasets that you have, these were sort of uncorrelated, right? Like it's not like, these two are very similar datasets. These are in fact like very different. And so that must always be the case, but we can't actually guarantee that, right? So it could be that these two are actually very much the same. So in that case, like all the trees would learn, would be trained on the same sort of data sets, and then they would all behave the same, and then you're basically like not making any sort of progress. And so basically increasing the number of trees. So those are like the cons. What are the pros? Think about it. If the probability of one of these guys failing is less than half, so it's like 0.3. In fact, even if it's more than half, it probably is still going to reduce it. So if it's 0.3, that's the probability of this guy failing, right? Not being able to make the correct prediction. And what's the probability that you will actually have the wrong prediction? Well, that's basically the probability that the number of trees that make the wrong prediction are bigger than or equal. So yeah, bigger than or equal to something comparable to the half the size of the data set, right? So in case of an odd number, that thing is actually like, yeah, so that thing is less than 0.5. So that's actually a nice thing. For example, in case of 3, that is actually like very, very less. But as things get bigger, you start to realize that okay, this doesn't always happen. But yeah, you can always do, you can like sort of do this thing. So how do I even say this thing? So if the probability of the tree failing is small enough, if it's actually less than, then notice that the ensemble Necessary insufficient condition for an ensemble to be more accurate than any of its individual is that classifiers are accurate and diverse. Diverse, probably thing up is pointing just random number really. Okay, so that's ensemble learning. Then you have the train validation test. You test on that, and then you do it for multiple different test data sets. So this is one fold you could do. This is another test data set that you could have, and the rest will be used for training obviously. And maybe this is another test data set that you could have. Obviously we have sort of shuffled these things before, so just so you know, and you just keep doing this, right? What that ensures is that your model is not just having this it's not just like performing well in one case. We are seeing like, so if that was a lucky case, and that's bad, right? Maybe like your model is performing really well on this case, but that was just because it got lucky. On average, how good is it performing? That's what we want to find, right? So we'll like move the test around, and yeah, right. So that's just the normal k-fold cross validation. Now, what happens when you're okay? There's another thing which needs to be accounted for. It's called hyperparameter tuning. So suppose you have trained your model. So suppose you have trained multiple models with different hyperparameters, and you have tested this on some unseen data set, and some of these models are doing bad. Well, you can clearly just discard those models, right? And then maybe choose the one with the best hyperparameter, right? But once again, we run into the same issue that the data sets that you have trained these models on, and and then the test data set that you have used, these basically determine which hyperparameter to use, sort of. Like it could be that the actual hyperparameter to choose that was not what you chose after doing this whole procedure, right? And so what we want to do is once again just move this. So move the split basically. So now you are talking about a train and validation split. So you train on something and then you validate on something else. So this is used for the hyperparameter training. So what you want to do is like you want to sort of move around the validation set, and then as you move around, you get basically different results. So suppose you just, let's just say you are thinking about decision trees, and then you use depth equal to 1 decision trees, right? So you will get different decision trees by training on different data sets like this, different trained data sets. Thing is changing, and you get like some accuracy. You take the mean of that, and that's the average accuracy for the depth equal to 1 thing. Similarly, you do something like that for depth equal to 2 and depth equal to 3 and so on. And now for these hyperparameters, you choose the best one, right? So that's the train validation thing going on, right? It's hyperparameter tuning with a bit of k-fold thing mixed in. So now what we want to do is like combine both of these. So you have the train test split, but now you actually do a train validation test split. So you split this thing first, the train validation and the test thing, and then inside of this train validation dataset, you shift the validation dataset, right? And then inside of that, you basically like hyperparameter tuning thing, find the best hyperparameter. Then you will train on the whole dataset, and then you'll use the final model to test on this, and that gives you the accuracy that should be, right? Yeah, cool. So this is just nested cross validation, by the way. Cool. So that's train validation test split. Then you have bagging and bootstrapping. All right. So bagging is basically like, okay, so you see that we shuffle the dataset all the time, right? The reason we do that is because we don't want like parts of the dataset to be like just completely filled with zeros and something like that, because that hampers the learning, right? we want to produce difficult examples in the training set, so that the model learns well, right? That's why we do this thing, this whole shuffling thing. Also, you want to have difficult example in the test as well, so that it's not like the model is just doing good but the questions are too easy, right? Okay. Yeah, so an obvious choice to split the dataset into smaller ones is by shuffling, but this still may cause high variance, not bias, for that reason, right? So yeah, this may still cause high variance for that reason. Better is to randomly sample with replacement for the dataset. Okay, sorry for the long pause. Just somebody came into my room and interrupted it. Anyway, what was I doing? An obvious choice is to split a dataset into smaller ones. So the obvious choice to do that is by shuffling, but this still may cause high variance, right? The reason is that when you shuffle, so how do I explain this? Maybe through example, right? Yeah, I don't know. I'll just state it, and then you can wonder why this happens, because I too am just wondering why this happens. And it ideally should not, right? But whatever. So this could still cause, and like basically, the part of it is still unseen though. Like you want your data sets to basically represent the original data set as much as possible, right? The original probability distribution as much as possible. So rather than shuffling, which is okay, which is like completely fine, what you could do is that you could randomly sample from the data set, and that's called back. So you just like have the main data set, and I just say that the rows are basically like the feature vectors. So you just take this row, you don't take that row, you take this row, maybe you take this row, you don't take that row, and so on. So you just like randomly like sample from this data set, and that's going to create a smaller data set, right? And so we'll train on that now, and then once you have trained on that, you once again you once again do this thing and you get the test data set, and then you test on that or something like that, right? So this is called bagging, and this is used in ensembles. So like whenever you are splitting the data, basically not splitting the data, that sounds like you have to include everything, but more like when you're creating smaller versions of the data set, that's a better way to describe it. You do that by bagging and not by shuffling. All right, not by like shuffling and splitting, basically. Cool. The better way is to be over there. Cool. Is to randomly sample. Yeah. So next we have like for large number of classifiers, in a sense the amount of data that we are actually using is actual. This shouldn't be the thing, its spelling is wrong. Using is more than that, right? So it's pretty obvious that the more number of these small data sets that you create, the more of the original data set is like used, right? So let's just say that your small n is like sort of, so let's just say capital N is the total number of rows for this thing, and small n is somehow small is the number of classifiers that you will be training. So that will require small and bagged data set things, right? Small and smaller data sets. So small n of these, and let's just say that small n is approximately, I shouldn't say approximately, let's just say it's of the order of n, right? And that's a bad notation, so we could probably say that natural log of this is similar to natural, I'm not even saying it's equal, I'm just saying it's similar to natural log of capital N. right? So they are on the same size basically, right? So if that happens, then you can do this argumentation that the probability that in one what was I fucking going to do? Right, I kind of forgot what I was going to do, right? Right, I certainly forgot what I was going to do. So you want to just randomly sample this guy, right? Oh, I think this one is sort of wrong. So this is the amount of data that we are actually using is more than, so this is just for one bagging, right? Yes, I'm just gonna getting a sample data set as bagging, basically bagging. So to bag once, the probability, so okay, so just to bag one instance, the probability that a particular instance is chosen is just 1 upon n. Probably that it's not chosen is 1 minus that, right? Yeah, let's just say that the size of this thing is I don't know, it's comparable to capital N. Okay, let's just say that this size is like capital M, right? And then you do n such things, and then let's just say that n times of capital M is equal to n, right? So then this would be just this thing times capital M and that power of n. So that's the probability that one particular row is not used throughout the whole thing, right? I shouldn't be saying this. Fine. Value. So for large sets, in a sense, the amount of data that we are actually using is more than, not more than, it is approximately. Actually, so this is like m times of n because you have n such supposed to be the actual data set, right? Thing 1 minus e power negative 1, that's a set which is used basically. That's what I've written over here. Okay, now it makes more sense. Fine. but that's just 1 in any case. This is just a thing, right? So just multiply by that, right? Yeah, so rather than taking like the expected value of just the log of p thing, you could just modify your p and then do the thing. What that will ensure is that you're basically like thinking about modifying your data set by like repeating some rows in a sense, and and that is like similar to this calculation. Yeah. Right. So the thing is that we do this so that UI such that you have because error incorrect, and then upon responding to these examples. because you're giving more emphasis to the problems which are hard. So yeah, right. So for actually like predicting for some particular small x vector, so what should we do now, right? X vector, and we'll get some prediction, right? And then for these predictions, let's just call these predictions as h or h sub m. So you have like 1 2 till m of equal to 1 till capital M of these models, right? So you will have h sub m for m is between 1 and capital M, such predictions, right? Yeah. And then you will just like average these according, so average these weighted with alpha, right? And then you will like take a round. So in the lecture notes it was given as, so in the lecture slides more like it was given more like sine of this thing, of this mean, or sum is more like, it's not even the mean actually, of this weighted sum. But because h could be scaled, right? So it would be completely okay. I think the reason that we do this sine thing is so that this has expected value equal to 0. Yeah. So the prediction use this thing. Right. Once again, what's alpha? By the way, alpha is just half natural log of summation of wi correct, and then upon summation of wi incorrect. Cool. Right. And I suppose we should be actually dividing this by summation of alpha m again, right? So this is not just a weighted sum, it should be a weighted mean actually. But yeah, because otherwise it wouldn't make sense. I think so. I mean, yeah, think about it. So right, what we kind of want is that like eventually you would have more correct than incorrect, so this thing would just be positive all the time. Yeah. And if that happens, well, these alpha thing summation, that should also be positive. But it could be that this thing is like extremely negative at one point and then everything is messed up. So I think that's why this thing is not included. But it doesn't hurt to be adding a mod over there, and then you can always do this thing. I guess, yeah, I mean, it's gonna work out. So then you can just actually apply a round over there, and so without all that you should be applying a sign. This is only for binary classification so far. It's like -1 and 1. Take true as 1 and false as -1 and then do this thing, but I guess we could extend it, who knows. So that's just ADA boost algorithm. Next, so boosting is done. Random forest. So just like in bagging, we also bag m features out of the total capital M features from the main dataset while creating smaller datasets. So remember ensemble learning, what we were doing is like we were creating these sample datasets, and then we were learning models on these sample datasets, and then we were using those to predict, and then those predictions were used to get the actual prediction, right? The way we were creating these datasets is like just sampling over the rows, choosing some rows basically. What if we choose some rows and at the same time we also choose only some columns? In that way it sort of like ensures that that your that these trees are sort of independent. That is, assuming your features are actually independent, then these trees will really be independent, because you are missing a lot of features. So it's like these are forced to learn some way to relate the target. They don't have access to the more useful features sometimes, right? So this is computationally better, obviously, because you have less features for each tree. Also, this ensures independent models. Ensures is a very big word to say, but yes, it kind of increases the probability of it being independent. Once again, this is done to reduce variance, right? So once again, remember that ensemble learning is mainly done to reduce variance for decision trees, right? This too is done to reduce the variance. So you want it such that like it, you know, it gives you more variety in the data sets, and so your model has to, how do I say this thing? I don't know how to say this thing. And then you sort of take a mean. So and then over here using features C and D, and then let's just say that this thing is, just one of the leaf nodes, so not splitting anymore, right? Cool. that's your Gaussian basis. So mu and sigma square are hyperparameters over there. Sorry, mu I is not a hyperparameter. It's this thing. The actual hyperparameter and the distribution's standard deviation is also a hyperparameter. Okay, cool. So higher sigma square, which is also called the variance, obviously gives a higher variance. Pretty obvious. Yeah. Okay. These features for different omega vectors. So you just generate these features for different omega, and that's your data set basically. Okay, cool. Miscellaneous. To calculate the gradient of function using Python to do this thing. Okay, so dot gradient f arguments is this thing, or you can dot. I don't think this will be asked. It will be more like a theory question, I guess. A theory paper, I guess. So yeah, I guess we are done. In fact, so it's a bit too late to be starting questions right now. So I'll just skip that. Yeah, so I'll see you guys in the next video. Bye.